So we now know that the transformation between the coordinates is linear. And we're now going to derive that transformation. And it's known as the Lorentz transformation. And it's the key of special relativity. And it's where the implications and consequences come from. So we're thinking about two frames, S and S bar, which is moving away with velocity u. And note we're free to choose the origin of these frames in space and time. So we choose we make the choice that at time 0 in S and S bar, the two origins coincide in space. Okay, and with that, we can write down, because we know the transformation is linear, that x bar, okay, some coordinate in S bar, can be written in terms of the coordinates in the unbarred system in a linear manner. And we know we've got four coordinates. We've got x, we've got y, we've got z, and we've got time. Okay. And a, b, c, and d are constants. Okay. Now if we think about the coordinate differential, dx bar, this will be a dx plus b dy plus c dz plus d dt. And we know that for the coordinate differentials, we have the ds squared is dx squared plus dy squared plus dz squared minus c squared dt squared is invariant. But because the coordinate differential and the coordinates satisfy the same transformation, then this must be true for the coordinates themselves. So we must have that x bar squared plus y bar squared plus z bar squared minus c squared t bar squared equals x squared plus y squared plus z squared minus c squared t squared. Okay, and let's try and find a solution in which y bar equals y and z bar equals z to just confine ourselves to one spatial dimension and one time coordinate. So one spatial coordinate and one time coordinate. So let's find a solution. Okay, so if in this case then we're only interested in the x bar and the cdt bar and the x and the cdt. So we're thinking about some transformation that lets us write our x bar in terms of 1 power of x and 1 power of t. And let's give it constants a and b. Okay, and this b is not the same as this b, so forget about this. We're now into the special case where we're only considering x and t. And t bar equals c x plus d t. Okay, so our barred coordinates x and t equals some constant times unbarred x plus some constant times unbarred t, and some constant times unbarred x plus some constant times unbarred t. Okay, so the goal is to try and find these constants. Find a, b, c, and d. Okay, and we're going to do that together. Okay, so we're thinking about two frames, S and S bar, which is moving away with velocity u. We've said that the origins of these two frames coincide when t equals t bar equals 0. So with this information, we've got our three equations. We know that x bar and t bar can be written as a linear combination of the unbarred coordinates x and t with four constants that we need to determine. And we also have this invariance relationship. Okay, so we've got three equations in three equations in four unknowns. which initially seems impossible, but of course we've got extra information about our setup. So let's think about equation 1, and let's think about the origin of frame S bar. So this is the origin of frame S bar. Its coordinate x bar equals 0. So if you're sitting at the origin of S bar, you see that your coordinate is 0, as observed by you. But if your friend is sitting in frame S, then they measure your coordinate to be some x, and this x equals what? So you're sitting at the origin of S, and you see this frame S bar moving away from you with velocity u. So at some general time t, not equal to 0, this coordinate of S bar will have moved a distance from the coordinate of S, and the distance is just u times t. Okay, u is the magnitude of this velocity. So with this in equation 1, we see that x bar equals 0, so 0 equals a times x, and x is ut, plus bt. Okay, so this tells us that b is minus a times u. Okay, so we've got one of our constants already, or eliminated one. So that lets us rewrite equation 1. So it's now x bar equals a x minus, instead of bt, we have minus a ut, so we can take the I at the front, and we've got a ut. And let's call this equation 4. Okay, so now we've got 3 equations. We've got the t-bar, we've got this invariance, and we've got x-bar. And we've got a, d, and e to be determined. So 3 equations, 3 unknowns, so we can solve this, and it's just a matter of some algebra. So let's proceed, and I want you guys to do this with me. So take a piece of pen and a piece of paper, and let's substitute x bar and t bar, so equations 4 and 2, into equation 3. So for x bar and t bar on the left hand side here, let's substitute x bar and t bar. And let's collect terms in x squared, t squared, and the cross terms xt. Okay, so go ahead and do this. Okay, so if you do this, then you'll get 3 equations. You'll get one that says that c squared d squared equals a squared minus 1. And let's call this equation 5. You'll get an equation that says that c squared d times e equals minus a squared u, and let's call this equation 6. And finally, you should have found that you get c squared e squared equals a squared u squared plus c squared. Let's call this equation 7. Okay, so we've got 3 equations with d, a, and e in them. Okay, and c is the speed of light here. Okay, so what do we do? Let's think about equation 6. This has a c squared and an e squared in it, so let's try and get an e squared from 6. So let's square equation 6. So 6 squared gives us that c squared d squared. So we've squared the c squared, so we get a c to the 4. So there's a c squared d squared. We've also got a c squared e squared. That gives us 4 powers of c equals a to the power 4 u squared. Okay, and now you see that c squared d squared is what appears in equation 5, and c squared e squared is what appears in equation 7. So we can substitute 5 in here, and this is 7. So this tells us that, so c squared d squared is a squared minus 1 times c squared e squared. It's a squared u squared plus c squared equals a to the power 4 u squared. So this is an equation just in terms of a, so this will give us what a is. Okay, so if you keep going, multiply this out, then you'll find that a, you should find, is either plus or minus 1 over the square root of 1 minus u squared over c squared. Okay, so we have to determine the sign, and we do that by saying that as the coordinates, as the two frames overlap, so if we reduce the velocity u to 0, then s bar is the same frame as s. Okay, so we found that a equals plus 1 over the square root of 1 minus u squared over c squared. So now we have a, we can find d by just using equation 5. So if you go ahead with your pen and paper and substitute a into equation 5, let's work out d. Okay, so press pause, do this and come back. Okay, you will have hopefully found that d equals plus or minus, and there's a u over c squared, and then we've got the same denominator, square root of 1 minus u squared over c squared. Okay, so now we have a and d, and we're going to determine the sign in a second, but let's move on to finding e. So we've got a and d and some equations with a, d and e, so let's pick equation 6 and find e. So go ahead and substitute a and d into equation 6 to find e. Okay, so press pause, have a go yourself, and come back. And hopefully you will have found that e equals minus plus 1 over the same denominator, 1 minus u squared over c squared. Okay, these signs we have to determine. So if we think about our two frames, if our velocity u goes to 0, then these two frames overlap. So if we look at equation 2, which involves t bar and t, then as the two frames overlap, as u goes to 0, this requires us to take the positive sign here for e. Okay, so the t bar equals t at the origin. And if you then use a and e in this equation 3, you'll find that you need to take the minus sign for d for equation 3 to hold. Okay, so this fixes our signs. We have a plus, we have a minus, and we have a plus. Okay, so these are the constants that we need to tell us how the unbarred coordinates x and t transform to the new barred coordinates in the new frame s bar. So let me now just clean this up. I'll rub this out and write down what we found in a summarized form. And we'll see the profound implications of such a transformation. Okay? Okay, so we found our three constants, a, d, and e. And we see that they all have the same, they all have the same denominator. So they all have this 1 over 1 minus u squared over c squared. So let's introduce some quantity we call gamma, and it depends on the speed u at which the two frames are moving apart. And this is defined by 1 over 1 square root of 1 minus u squared over c squared. Okay, so this is our gamma Lorentz factor. Okay, so let's summarize what we found. We found that x bar, so the coordinate as measured in frame s bar, is equal to a, and that's just gamma, x minus u t. So these are the unbarred coordinates corresponding to frame s. We said that y bar equaled y and z bar equals z. Okay, so this is the solution for this case. And our t bar is equal to, so there's an et and a dx. So both e and d have this gamma factor. So we can take gamma out the front. And we have et. Okay, so e is just equal to a, which just equals gamma. So this is t. And then d has this minus u over c squared in front of it. U over c squared at x. Okay, so these are our Lorentz transformations. Okay, and these are the transformations derived from the setup in which we had two frames. One was moving away from the other with velocity u, and their origins coincided at time t equals t bar equals 0. Okay, and the frame was moving away in the x direction. Okay, so let's think about a sanity check. When the velocity u goes to 0, or more precisely, when u over c goes to 0, then we should get back our old Galilean transformations. Okay, so the world that we know moving at slow velocities should re-emerge. So as u over c goes to 0, this gamma factor, it goes to what? It goes to 1. And our two equations tell us that t bar equals t, and that x bar equals gamma, which is 1, x minus u t. And this is the old Galilean transformations. Okay, so the old world of Galileo and Newton is recovered if we consider small velocities at which the two frames depart. Okay, this is all good. And then we note something else. We note that if u is greater than c, then this thing becomes imaginary, gamma, and these equations become unphysical. So the Lorentz transformations become unphysical. So we have a speed limit, okay, and it's given by the speed of light, and anything that travels faster than that doesn't belong in our physical universe, certainly the one that we experience. Okay. So here we have our Lorentz transformation. This takes us from the unbarred coordinates to the barred coordinates. But what if we want to go the other way? So what's the inverse transformation? And the best way to do this, or the simplest way, is just to relabel our two frames. So let's relabel, let's call S bar, and let's call S bar S. And if we do that, then if you sit yourself at the coordinate of S bar, you will see, and you're now calling this frame S, you will see S bar moving away from you with a velocity minus u. Okay, so we need to change the direction of our velocity also. Okay, and if we work this through, then we just can write down our inverse transformation. And the inverse transformations are that x equals gamma x bar plus ut, and that t unbarred coordinate equals gamma t bar plus ux over c squared. Okay, so sometimes we'll want to work with the inverse transformation, sometimes with the direct. So before we look at the consequences, let me just write down a more convenient and easier to remember form for these guys. So for the case in which s bar moves away from s with a constant velocity u along the x direction of s, under the condition that the origins overlap or coincide at t equals t bar equals 0, and this is called the standard configuration. We found that just by using the special principles of relativity, that the speed of light is invariant in all inertial reference frames, and that the laws of physics, so all of physics, should apply in all inertial reference frames. We found that the coordinates should transform in a linear manner, and the linear transformation is given here, and this is our Lorentz transformation for the standard configuration in which the frames are moving away from each other like this. The symmetry in the problem is a bit hidden here. It's a bit nicer if we introduce some extra quantities. So we've already seen gamma. This is 1 minus 1 u squared over c squared. Okay, that's what this gamma is. And then let's also introduce beta. And beta is defined by u over c. Okay, it's a dimensionless quantity. So the ratio of two speeds. So the speed the frame's moving away and the speed of light. And if we use these, then we can write down the transformation in a matrix form. And we think about coordinates c, t bar, x bar, y bar, and z bar. And the Lorentz transformation matrix involves x and t get modified, but y bar and z bar are constant in this case. So it's only the upper 2 by 2 matrix. So this is a 4 by 4 matrix. Okay, and it's acting on c, t, x, y, and z. Okay, so y bar and z bar are unchanged. So we have a 1 here and a 1 here and zeros in these places. 0 and 0. And it's only x and t that kind of get modified. And with gamma and beta introduced, we can just write this as gamma, gamma, and then we have a minus gamma beta. Okay, so you can see this for yourself. C t bar, okay, it's c times this thing, which equals gamma ct minus beta x. Okay, so c times u over c squared is u over c, which is beta. So ct bar is gamma times ct minus gamma beta x. Okay, and yes, I forgot the gamma acting on ux over c squared. So there's a gamma beta x. Okay, and x bar equals gamma times x minus gamma beta ct. So this is gamma x minus gamma, and u is equal to beta times c t. Okay, so that's consistent. Okay, so this is the way I remember it. So you only need to think about gammas along this diagonal and minus gamma beta along this diagonal. Okay, so you only need to remember two things: gamma and minus gamma beta, and remember that it's symmetrical. Okay, this is the standard configuration. In your notes, we also go through the Lorentz transformation in a general case where the frame S bar moves away from S in some general direction, not just along the X direction. So this will be the vector form of the Lorentz transformation. I'm not going to go through this here because it's a bit tedious. It's not that interesting, and it'll be more exciting and interesting to move to the consequences of the Lorentz transformations. Okay, but please don't ignore that in the notes. The notes are detailed, and we'll take you through step by step, so please read those. Okay, so that's on the vector form of the Lorentz transformations. So see your notes. Okay, some of you maybe all of you may be thinking, what's this got to do with tensor algebra? Why do we do the tensor algebra before doing this? Because it seems a bit different. But after we look at the consequences of the Lorentz transformations, we'll rewrite them in a covariant form. Okay, so with our subscripts and superscripts and metrics and the likes. Okay, but for now, let's just think about the consequences of these transformations.